All right, so we're diving deep today, tackling a question that seems super basic at first, but it's actually pretty profound when you think about it. Why is the Earth round?
You got it. We're going way beyond just saying gravity
Hmm.
and really unpacking how our planet got its shape. We're going to look at the whole story of the solar system's formation, the forces at play, and all this cool evidence from both history and modern science.
Yeah, no flat Earth theories here. We're talking hardcore physics. So to kick things off, we got to rewind the clock, like 4.6 billion years. Back then, there was this massive cloud of gas and dust called the solar nebula.
Exactly. And something, probably a nearby supernova, caused this cloud to collapse. Now, here's where things get interesting. As it collapsed, it also started to spin.
Okay, so imagine a figure skater, right? When they pull their arms in, they spin faster. It's the same principle here, conservation of angular momentum. As this nebula contracted under its own gravity, it spun faster and faster, naturally flattening into a disk shape.
And that disk shape was crucial. That's basically the blueprint for our entire solar system, setting the stage for where planets would eventually form. Now, within this swirling disk, tiny particles of dust started bumping into each other and sticking together.
Like a cosmic game of sticky snowflakes or something?
Sort of. These little clumps called planetesimals are like the building blocks of planets. Over millions of years, these planetesimals kept colliding and merging, getting bigger and bigger. That process is called accretion, and that's how Earth grew.
So it's like a cosmic demolition derby, but instead of smashing things to bits, you're creating something huge.
Precisely. And the whole time, gravity's working behind the scenes, pulling in more and more material, guiding this whole process. It's fascinating how the temperature differences within the disk also played a role, right?
Yeah. Like closer to the sun, it was way too hot for the lighter elements to hang around, so you ended up with the rocky planets like Earth.
Right. And further out, where it was colder, you got those gas giants like Jupiter and Saturn. Now, the early Earth was hot, I mean super hot, molten, basically a giant ball of liquid rock and metal.
And that molten state is key to why the Earth's round, right?
Absolutely. Think about it. Gravity pulls equally from all directions towards the center of mass. So when you have a molten ball, the only way for everything to settle is in a sphere. That's the most stable, the most energy-efficient shape you can get.
Makes sense. A sphere minimizes the surface area for a given volume, so it's all about finding that perfect balance.
Exactly. Plus, this molten phase allowed the Earth to differentiate. The denser material, like iron and nickel, sank to the center, forming the core, while the lighter stuff rose to the surface, forming the mantle and eventually the crust.
So gravity isn't just holding us down, it's like the cosmic sculptor, shaping planets from the inside out.
Right. And for any object massive enough, gravity will overcome any other forces, molding it into a sphere. That's what we call hydrostatic equilibrium. In fact, that's one of the things that actually defines a planet.
Yeah.
Smaller objects, like asteroids, don't have enough gravity to overcome their own rigidity, so they end up lumpy and irregular.
Which is why asteroids kind of look like giant space potatoes. But if you look around our solar system, it's clear that this whole sphere thing isn't just an Earth thing.
Oh, definitely. All the major planets are spherical, or nearly so. But planets that rotate, like Earth, they're not perfectly round. They bulge a bit at the equator due to the centrifugal force created by spinning.
Yeah, like when you spin a ball of dough, it flattens out a bit. The faster the spin, the more pronounced the bulge.
It's amazing to think that way before we could see Earth from space, people already figured out it was round. The ancient Greeks, for example, they were brilliant observers.
Yeah, they noticed that during a lunar eclipse, Earth's shadow on the moon was always round. That's a pretty big clue right there.
Definitely. And Aristotle, he observed a couple of other things, like when ships sailed away, they disappeared hull first over the horizon. That wouldn't happen on a flat surface. Plus, the fact that you see different stars in the sky depending on where you are on Earth.
And then there's Eratosthenes. He actually calculated the Earth's circumference, like way back in 240 BCE, just by comparing the lengths of shadows in two different cities on the same day.
That's incredible. It really shows you the power of observation and deduction. But of course, the ultimate proof came centuries later when Magellan and Elcano circumnavigated the globe. They literally sailed all the way around, proving beyond doubt that the Earth is a sphere.
And now we have satellites and astronauts giving us those breathtaking pictures of our blue marble hanging in space. Plus, think about things like time zones. They only make sense on a rotating sphere.
And weather patterns, too. The Coriolis effect, which makes storms spin in different directions in the northern and southern hemispheres, is entirely due to the Earth's rotation as a sphere. Even engineers have to factor in the Earth's curvature when they're building large structures.
So we've come full circle. It all goes back to gravity, the initial conditions of our solar system, and this incredibly long process of accretion. It's mind-blowing how this fundamental force, acting over billions of years, has shaped our home into this, well, seemingly simple shape.
Absolutely.
Hmm.
It makes you wonder what other seemingly simple shapes or phenomena in the universe have incredibly complex origins, perhaps shaped by forces we're only just beginning to understand.